Good morning, everybody. I'm glad to see you, and maybe you glad to hear me. Today we will discuss with you the most romantic topic of physics. Start to learn this topic. This is the hemodynamics. To begin with, we will analyze the word hemodynamics with you. And this word is Greek and consists of two words, gem, this is blood, and dynamos, this is a movement, power, dynamic. And what does it mean? This means that we will study the movement of blood in our body according to what laws the blood moves through our circulatory system, and we will also talk about liquids, viscosity, and other points. Let us now consider in more detail. And hemodynamics is the dynamics of blood flow, as we said earlier. Yeah? And hemodynamics is an important part of the physiology of cardiovascular system, dealing with the forces that the pump, our heart, must develop to circulate blood through the cardiovascular system. And adequate blood circulation, or our blood flow, is a prerequisite for an adequate supply of oxygen to all tissues. And we know with you that oxygen is the main element of our life. I think you know this information from biology, from chemistry, and other departments, maybe other lessons, without which we can't exist in our world, for example. Yeah, our blood is the most important fluid in our body, the most necessary liquid in our body. But you and I must figure out what is the blood. In fact, everything is not as simple as you think, because there is a general definition of what blood is that you should know. Let's take a look at it. Blood is the body fluid of humans and other animals, maybe our cats, our dogs, and other animals, which delivers the necessary substances, nutrients, oxygen to the cells, and transports metabolic products from the same cells. That's right, this is actually the case. But this definition is still more medical. You and I need to deal with the physical part. The most important thing that you have to understand is blood liquid or is it not liquid? If it is liquid, what is it? If not liquid, then what? How can it not be liquid at all? You should be interested in such questions for the moment, and I must answer on these questions. Blood is fluid or not fluid? So, let's figure it out. I think you know this, that blood is made up of blood cells suspended in blood plasma. In total, there are three main types of blood cells. I think you know these cells. These are red blood cells, the most number of cells in our blood is red blood cells, RBC, or other name is erythrocytes. Their number is 45% of the total blood mass, total blood number. In another way, they are also called erythrocytes, how I said. Thanks to them, the color of our blood is red because they contain hem, which contains iron. Hem and globin, It stains the blood red. The next type of blood cells, the second and third part, can you see, is white blood cells, WBC, or leukocytes. And these are the main defenders our main fighters against infections, immune cells, yeah? And the third type of cells is platelets. Platelets are responsible for a very important process in our body, stopping bleeding. And there are few total leukocytes and platelets in our body compared to erythrocytes. They are only 1% of a total blood composition. So small number, yeah, only 1%. What do we get as a result? 46% of the blood is blood cells. And I think you know that they are bodies. They are not liquid. That is, it turns out that 46% of our blood is not liquid. Really, 46%. And thus, the liquid part of blood, this is plasma, is only 54%. This means that you need to be more careful with the loss of hydrodynamics in the vessels of our body, because our body has a large and small vessels, and the loss of hydrodynamics work well only with blood flow through large vessels. There will be errors on small vessels. Please don't forget about it and be careful with this. So now let's take a closer look at our circulatory system through which blood moves. The human cardiovascular system is a closed system for pumping blood in which there is a pump, the heart. There is a pump, heart, and pipes, vessels, many vessels in our body, through which blood moves. In our body, there are three types of vessels: arteries, veins, and capillaries. The heart is a hollow organ with 4 chambers. There are 2 atria, right and left, and 2 ventricles, right and left too. The main functions of the human cardiovascular system are: there are 2 main functions. First function is delivery of nutrients, oxygen, and heat flow to tissues and organs. And the second function is outflow from tissues, from organs of metabolic products, primarily carbon dioxide. In the picture on the slide, in this picture, the name of this picture, heart and circulation, you can see a diagram of human cardiovascular system. In our body, blood does not circulate as it pleases. The blood always moves in a strictly defined direction along strictly defined path. There are 2 main pathways of blood movement in our body. They are called the large and the small circle of blood circulation, the large and small, large and small. So let's take an example of the movement of blood through the system, and let's start with a large circle of blood circulation. The systemic circulation, large circulation, begins in the left atrium. Here. Left atrium. One vessel leaves the left atrium, the largest vessel in our body. This is aorta. And don't forget, aorta is the artery. This part, aorta, goes from left ventricle. Oh, left atrium, sorry. Left ventricle, sorry. Left ventricle. So, from the aorta, blood sequentially enters the arteries of a smaller diameter. Next arteries with a smaller diameter. Then into arterioles. Arterioles they are small arteries and comes to the capillaries. Let's not forget that the most important thing, the blood from the left atrium comes out rich in oxygen, and it's not for nothing that it is marked in red on the diagram. You can see red part, red color. What happens in the capillaries? And blood come to capillaries, body cells, capillaries. So capillaries are the smallest vessel in our body, and they have the smallest diameter, only from 4 to 7 microns, as well as the thinnest wall. What is it for? Everything is simple in order to maximize its main function, gas exchange. The main function of capillaries is gas exchange. This means that blood rich in oxygen and nutrients entered the capillaries of the systemic circulation in order to give the cells everything they need and take away from the cells unnecessary metabolic products. So from circulation to cells come oxygen and nutrients, and out from cells and come to capillaries go unnecessary part, metabolic products. The gas exchange process took place in the capillaries, and the blood has already become rich in carbon dioxide. In the diagram, it's marked in blue part. Let's see. Oxygen come to cells, and carboxygen come out from cells. They go out from cells and come to capillaries and venules and veins too. Where next? And then the blood from capillaries of the systemic circulation enter to venules. After that, veins, and collecting in two large veins, the superior and inferior vena cava. And vena cava superior, vena cava inferior in lingua latina. Yeah? Flows into the right atrium, where the systemic circulation end. Right atrium, yeah? It comes from the left ventricle to right atrium. Where the systemic circulation ends, yeah? Then, from the right atrium through the tricuspid valve, blood enters in the right ventricle. So from the here, and in which the pulmonary circulation begins. From the right ventricle comes one large vessel, the pulmonary trunk. This is artery 2. Pulmonary trunk start from the right ventricle, which is almost immediately divided into two large arteries, the right and left pulmonary arteries. It divides after ending, yeah, on the right and the left pulmonary arteries. Don't forget, please, that the blood from the right atrium came out rich in carbon dioxide, and in the picture it's also indicated in blue. You can see this is the blue part with carbon dioxide. So further, from the arteries of the pulmonary circulation, blood entered the arterioles and came to capillaries of pulmonary circulation. This is a small circulation, yeah? Circle. And again, there, by analogy with a large circle of blood circulation, the process of gas exchange take place. There is only one difference, one difference. Now, carbon dioxide and metabolic products leave the capillaries, while oxygen and nutrients enter to the capillaries. Now, the blood, rich in oxygen and nutrients, from the capillaries of the pulmonary circulation, enters the venules, veins, and through the 4 pulmonary veins, number 4 pulmonary veins, enters the left atrium, where the pulmonary circulation ends in the left atrium. After that, through the mitral or bicuspid valve, the blood enters the left ventricle, where the systemic circulation begins again. And since the systemic circulation provides blood flow to all tissues of the body except the lungs, it's also called enhanced circulation or peripheral circulation. About 48% of the total blood volume of the body is in the systemic circulation, and only 16% in the heart and lungs in pulmonary circulation. Please don't forget about it. Don't forget about it. So now let's move on to the liquid. What is the liquid? Liquids is the general name of two states of matter, liquid and gaseous, characterized by the absence of long-range odor and a high degree of mobility at the molecular level or molecular scale. So, one of the main physical characteristics of a fluid is density. To calculate the density of a liquid, we need to divide the mass of our liquid, for example, by the volume on this liquid. V, yeah? M divided by V. You can see this formula, yeah, now on the slide. The density of liquid characterizes as the number of molecules of a substance per unit volume. And the Greek letter rho. Density, we mark Greek letter rho. Greek letter rho, the name of this letter. So don't forget about System International units of density. You can see it is kilogram divided by meter cube. Don't forget about it, please. System International units of density is kilogram divided by meter cube. Don't forget, please. Let's move on to other physical characteristic of liquid. And there are many fluids around us and within us. Some of them are moving, some, on the contrary, are at rest. But all liquids have weight, which means they put pressure on the bottom and walls on the vessel or other bodies here in which they will be located. This is Pascal's law. What Pascal's law describes to us. Pascal's principles. It sounds like this. The pressure on the surface of liquid produced by external forces is transmitted by the liquid equally in all directions. You can see. Pressure applied on one point of liquid transmits equally in all direction. In any body, if fluid or water or other fluids may be in any bodies, and so Pascal principle can work in everything, in everywhere. So next, we know with you that pressure in solid, yeah, for example, let's talk about pressure. Next physical characteristic is pressure. And I think you remember that pressure in solid materials is a force that acts on a unit area. You can see the formula in the top of right corner, yeah? Now, let's try to calculate the pressure of a resting immobile liquid on the bottom and walls on the vessel. Consider the picture on the slide, this part, on the left part. So, let's see, this is the body, yeah, maybe the vessel, or the vessel contains a liquid, the height of the column, which will be denoted as H. H. This is the height of this column. So the base of the vessels has an area A. Area A is the same, these two. The liquid and the vessel are motionless, which means that its weight is equal to the force of gravity. Now, the force F with which the liquid pushes against the bottom of the vessel is the weight of the liquid. And we can calculate it by formula. Omega is the weight, F gravity is the F gravity, the same, yeah? And what is about F gravity? This is mass multiplied on gravity G, yeah? Gravity coefficient G. Also, recall the formula for finding the mass of a body through the density of its substance and volume. From this, don't forget about it. How can we calculate mass? We must density multiply on volume. So let's put it in spite of m here. And so the volume of a body, yeah, how can we calculate volume of a body V? Let's see. This is a parallelepiped, can we say? And as a result, we must remember the formula. How can we calculate the volume of this figure? We must take the area and multiply it on the height of this column of this body. So we must put it in spite of V. And what happened? After that, as a result, pressure, we have the equality. Pressure in liquid is rho, the density of liquid, multiply on gravity coefficient G, and multiply on the height of liquid. And we can calculate the pressure, the static fluid pressure after that. Let's continue. It was the static fluid pressure. And we must not forget about units, about system international units of pressure. I think you know that this is Pascal. What is about Pascal? Pascal is Newton divided by meter square. So, there are other non-systemic units of pressure which we can use. For example, another units may be bar. Let's see the ratio that 1 bar is 100 kilopascal. Don't forget about it. And also pressure can be measured in atmospheric units, in atmosphere. That 1 atmosphere is near 100 kilopascal too. 100 kilopascal too. So the 10 in the power 5 Pascal, and it's 760 millimeter mercury. And little more about that. We know that we are used to measuring the blood pressure in our body as well as atmospheric pressure, not in Pascal, but in completely different units. This is a millimeter mercury. Historically, pressure was previously measured with mercury tonometers for a long time. And how do 1 millimeter mercury correlate? Let's see. 1 Pascal or 1 atmosphere. What happened? Let's figure it out. Let's remember the ratio. 1 millimeter mercury is 133 Pascal. Let's also remember the normal atmospheric pressure we are used to 716 millimeter mercury. Now, much will it be in Pascal? Let's remember the ratio. 760 millimeter mercury is the 10 to the power 5 Pascal. So this is 1 atmosphere. Don't forget. Don't forget about the one important principle of hydrodynamics. This is well-known principle of Archimedes or Archimedes principle. To begin with, consider the definition of an important force, the Archimedes force. A body immersed in a liquid or gas is subjected to an ejection or lifting force equal to the weight of the volume of the liquid or gas displaced by a part of the body immersed in liquid or gas. The law was discovered by Archimedes in the 3rd century before our. And the force of Archimedes is also called the ejection force. The ejection force is also always upward. What is the reason for the emergence of such a force and its origin? If we look at drawing, we will see that the object is partially in liquid, and the ejection force is directed from the water into air. Buoyant force or ejection force. The force of the liquid pressure from below is greater than the pressure from above. This force is greater than the above pressure. Therefore, the result is a force that pushes body out of the fluid is Archimedes force. This is the Archimedes force will be. You can see the formula on the slide. The most important thing in this in volume. The volume, volume. I wrote disp. What is about disp? Displaced volume. So Archimedes force is rho, density of water, multiply on gravity coefficient and multiply on volume of body. So the volume here should be only that part of the body that is immersed in liquid, or this volume is equal to the volume of displaced liquid. So I wrote displaced fluid. Volume of the fluid displaced by an object is the same number, with volume of body which are in water now. Up, down part, for example, we can see. So it was Archimedes' principle. Now, in order for us to understand the movement of liquid through our vessels or the movement of water through pipes, for example, in our kitchen maybe, in our bathroom maybe, we should discuss one important equation. This is a continuity equation. This part is very necessary for our body too. You will understand this information. So, consider an incompressible fluid. Let's take incompressible fluid. So, the continuity equation of fluid motion is the law of conservation of mass of an isolated system. You have the picture on the slide, Fluids follow from a wider pipe with a large cross-sectional area, A1, to a narrower pipe with a smaller cross-sectional area, A2. Let's compare, that A1 is more than A2. So, the fluid velocity in a wider pipe is V1, in a narrower one, V2. So let's compare. V1 is less than V2 because the area is most than area 1 is most than area 2. So pressure in the wider pipe P1, this pressure P1, and in the narrower pipe P2, narrower pipe P2. Then, since the liquid is incompressible, we said this, fluid is incompressible, liquid is incompressible, it turns out that the volumes V1 and V2 are equal, the same volumes. So let's substitute physical quantities in our equality, reduce and get the expression. How can this equation is how many times the cross-sectional area, lumen of vessel, of the pipe is smaller, the same number of times the velocity of the liquid flow in it will be greater and vice versa, or the pressure decreases in the direction of increasing the velocity of the liquid. You can see velocity first, we can multiply first velocity on first area of the first part is the same number velocity of second part and area of second part. So how can we take it? We can take it from the difference, from the same of volumes and complete it after some multiplications. And so we can say that this number multiplication between velocity of liquid and area is constant. And don't forget that we can see that since A1 is more than A2, how I said, it must be true that velocity 2 is more than velocity 1 and pressure 1 is more than pressure 2. Or can we say the pressure decrease in the direction the fluid velocity increase and vice versa too. Don't forget about it. And we shouldn't forget about a little refinement for our vessels. As you remember, I think you remember, that the largest vessel in our body is the aorta. You can see the numbers, The largest vessel. I think you know that the most diameter has the aorta of our vessels in our body. So, which means that it has the largest cross-sectional area, it's logically. The smallest vessel in our body is the capillary. We also discussed with you that the aorta and capillary are connected, because our cardiovascular system is closed. We said this information, you can see. So the aorta connect with capillaries through the cardiovascular system, through the arteries, arterioles, veins, and venules, and other. So let's continue. Now let's try to say a few words about rate of blood flow in the aorta and capillary. The blood flow rate in the aorta in the human body is also the highest, and the flow rate in the capillary is the smallest. So the gas exchange processes have time to pass. But according to the equation of continuity, the flow rate in the capillary should be greater than in the aorta, since it has a smaller cross-sectional area. But this does not correspond to the realities of our body. Then the question is, who is wrong? Who is wrong? Where is the mistake? What is the reason? Students, it's very simple. We forgot to clarify that in our bodies there is not one capillary. There are millions, billion capillary in our body. And they are all associated with aorta. And the human cardiovascular network is inseparable, united and closed, which means how much blood has passed through the aorta, the same amount of blood will pass through the all capillaries. And if we add up the cross-sectional areas of all capillaries, it turns out that the total cross-sectional area of all capillaries is 500 times larger than the cross-sectional area of the aorta. And according this continuity equation, it means that the blood flow rate in aorta is 500 times higher than in the capillaries, which corresponds to the real model of our body in the process of life, According to this table, you can see the area of vessels and velocity of some vessels. Using the continuity equation, you can calculate the velocity in arterioles, in venules, in small veins, and in vena cava, for example. We will try to calculate it on our practice lesson. And now, if we consider our vessels, then you and I know that our vessels differ in cross-sectional area, which, as it turned out, is important for us. Namely, it's important for the determine speed of blood movement. Yeah, and how we can say considering table. Yeah, I said that we can calculate this number in our practice lesson, and if you want, you can calculate it at home. You can do it, and after that you can say me right answers maybe, or if you will have questions, you can ask me. So let's continue, and our continue part is Bernoulli equation. Next equation is Bernoulli's equation. This is another important equation in general hydrodynamics. It's valid for stationary fluid, follows in which there are no viscous friction forces. Since our circular system in the body is unsteady, that is, it's constantly in a changeable state, therefore Bernoulli equation can be applied in hemodynamics, but with caution. Only for small sections of the circulatory system, while only time averaged values will be substituted into this equation. Bernoulli's equation is formulated as follows. What it is? For a stationary flow of an ideal fluid, the total pressure equal to the sum of static, dynamic, and hydrostatic pressures is the same in the all cross sections of the stream tube. And this equation states that the sum of all forms energy in a fluid following along a closed path is the same in any 2 points of this path. It looks like this. First part, P1, pressure energy, on the first point, plus kinetic energy per unit volume, and plus potential energy per unit volume. And we can see the first bottom. And the second bottom on the height Y2, yeah, the same with the second, yeah, and this is a constant. Energy per unit volume before, energy per unit volume after. Don't forget how much energy was, how much energy will be. The same number is constant. And now we must say about Bernoulli principle in human body. Suppose that the speed is the same everywhere on average. For this principle, we must take that velocity in all of our cardiovascular system is the same. So V constant. V constant must be. This is a model. This is only model. It's not real. It's model for best understanding and for calculating. So, with regard to the circulatory system, everything that is above the level of a heart experiences reduced static pressure, and this is in particular the brain. And everything below legs, for example, on the head and on the legs. So all our cardiovascular system starts from our heart. So, and heart is a zero level. Heart is a zero level. And we know, according to the Bernoulli's equation, the number of pressure on the heart line, on the heart level, is near 100 millimeter mercury. So, for the brain, the effect of hydrostatic pressure changes the static pressure by about 30 millimeter mercury. 30 millimeter mercury, less than this number, because the energy is necessary to go, to conduct the heart to the upper part. So must be energy, and so we must minus, must be minus. So less number of pressure will be less and near 70 millimeter mercury. Near 70 millimeter mercury. And as for about legs, this correction is about 110 millimeter mercuries, because go down, blood go down, it's very good for blood, and it go free and not take the energy for going for blood, going for conducting, and so we must plus 110 millimeter mercury, and so the pressure in our legs will be the most, and number 210 millimeter mercuries. Don't forget about it. You can see the calculations, according this Bernoulli equation. And we will talk about it on our practice lesson again, don't forget. So, but our circulatory system has regulatory mechanism that adjust for the supply of blood to organs that are in unequal conditions. So after talking with you about different types of pressure in liquid and blood, we should move on to talking about the viscosity of a liquid. What is about viscosity? This is an indicator of its resistance to gradual deformation. Definition. Viscosity of liquid is an indicator of its resistance to gradual deformation. Typically, dynamic viscosity is a measure of fluid's resistance to shear flow. If in two parallel or more parallel contacting layers the fluid moves with different velocities, like is in a picture, for example, the length of area, arrow, the most length of arrow, most number of speed, most number of velocity. So don't forget about it. And the fluid moves, layers with different velocities, V1, V2, V3, V4, and etc. Then the forces of viscous friction will act along the boundary of their contact. For the slower layer 2, for example, let's compare the first and the second part. So, for the slower layer 2, this layer 2, the viscous friction force is directed in such a way that it facilitates its faster movement. For a fast layer 1, the friction force is the force that slows it down. The force of interaction between layers is described by Newton's formula, and from Newton's formula we can express the formula for the viscosity coefficient, which has the form. This viscosity coefficient. Greek letter eta. This is Greek letter. The name of this Greek letter is eta. How can we calculate it? Through the Newton's law. F, force, divided by area multiplying velocity by what? By the diameter of our vessel, of our tube. So, or we can say about gradient, yeah? Where is the velocity gradient? This is the velocity gradient. Because we have a different velocities. And how can we calculate it? Using the gradient. Derivative of the fluid velocity in the direction perpendicular to the flow. On the basis of this expression, the derivative unit of the viscosity coefficient in the System International Unit is introduced 1 Pascal per second. Pascal per second. Don't forget about it. System International Unit is Pascal per second. Don't forget about it, please. How can we put it? We should put System International Units in spite of our physical quantities, and we can take Pascal per second. The relationship between dynamic viscosity and density of a fluid is known as kinematic viscosity. Don't forget about it. So, let's not forget that the viscosity of water at a temperature of 20 degrees of Celsius is 1 millipascal per second. 1 millipascal per second. And the viscosity of the blood of a healthy person is in the range from 4 to 5 millipascal per second. Normal numbers. Don't forget, please, this normal number, please. So let's continue. And we must say about classification of fluids. We divide liquids or fluids into two categories, Newtonian and non-Newtonian. Let's start from Newtonian. For Newtonian fluids, the viscosity coefficient depends only on the type of substance and temperature. Such liquids have a simple composition, inorganic molecules or low molecular weight organic molecules. Simple molecules are a relatively simple nature of the interaction of parallel layers of liquid. The viscosity of liquid depends only on temperature. As the temperature rises, viscosity index decreases. Temperature increases, viscosity decreases. There are, for example, such liquids may be water, gasoline, alcohol, human blood plasma. And what is about non-Newtonian liquids, non-Newtonian fluids? The viscosity coefficient of non-Newtonian fluids depends not only on temperature, but also on the features of their flow, the transverse dimensions of the flow, the velocity gradient in each. Such liquids are liquids with a complex molecular composition. Suspensions, emulsions, liquid with a high molecular composition, blood. Our blood is non-Newtonian liquid. Liquid plastic, ketchup are well known to you from the lessons of chemistry, I think. So this is non-Newtonian and Newtonian liquids was. Knowing of types of liquids, of fluids, we must talk about the types of movement of fluids through the pipes, through the vessels. And there are two types of fluid flow in our life. Laminar flow and turbulent flow. Let's start from laminar flow. Figure on the left. This flow is an ordered mode of fluid flow in which the fluid moves in layers without mixing, as if sliding among themselves. In laminar flow, the velocity, pressure, and other flow properties at each point in the fluid remain constant. Laminar flow can be through consisting of thin layers parallels to each other, you can see. The biggest arrow has the biggest velocity, and less velocity, less velocity. So in normal conditions, in our body, in our cardiovascular system, there is the laminar flow, but not everywhere. In aorta, in the heart, in the seats of dividing vessel, there is the turbulent flow. And what is about the turbulent flow? Or turbulent fluid of that flow? Picture on the right. B point. This is the vortex fluid flow, in which the fluid is subjected to uneven oscillations and mixing. In a turbulent flow, the fluid pressure changes from point to point. This is why we hear noises, sounds, We can hear noises and sounds. There's a noise from turbulent flow. And you ask me, how can we find out what type of fluid is in the tubes or vessels of our body, maybe? Yes, it's very simple. For this, there is a special formula for calculating the type of fluid. It's called the Reynolds number. It also asks to determine the type of fluid or blood flow at a particular moment in time. If we know the type of fluid, density, rho, fluid density, velocity of fluid flow, diameter of the tube, of the pipe or vessel, and the viscosity coefficient of moving fluid, letter eta. And after that, you can see the formula on the slide of Reynolds number. Rho, the density of fluid, multiply on velocity of fluid's flow, multiply on the diameter of tube, pipe, or vessel, and divide by viscosity coefficient eta. So, for each fluid, there is the critical value of Reynolds number, and which is as it were the boundary between the types of fluid flow, wherein if our Reynolds number less than critical number will be laminar flow. If more than our critical number will be turbulent flow, but between the interval will be unstable flow. Maybe laminar, maybe turbulent, maybe laminar, maybe again turbulent. So, and what is about information of our blood flow? When Reynolds number rise above 20 to 200, from 200 to 400, turbulent flow will occur at some branches of vessels, but will die out along the smooth portions of vessels. However, when Reynolds number rises above approximately 2000, turbulence will usually occur even in a straight, smooth vessel. In the proximal portions of aorta and pulmonary artery, Reynolds number can rise to several thousand during the rapid phase of ejection by ventricles. And what is about causes of turbulence? The first cause is high velocity of blood flow. Next is pulsative nature of the flow. Third is sudden change in vessel diameter. And the last, large vessel diameter. And don't forget, in small vessels, Reynolds number is almost never high enough to cause turbulence. Don't forget about it, please. So, now, knowing the types of fluid flow, we must talk about another important physical characteristics. This is resistance. Resistance of a circular pipe, of vessels. So, consider a situation where there is the round, smooth pipe. For a round, smooth pipe of length L and radius R, through which a liquid follows in a laminar flow with dynamic viscosity eta, Greek letter, the flow is related to the pressure drop in the pipe with resistance R. R is 8 multiplied on eta, L, the length of our tube, our vessel, divided by pi, and R, radius in the power 4. And so this is a liquid, and let's see how can resistance connect with the vessel. We know that vessels really has resistance, and blood flow has pressure, and this pressure connects on this vessel. And how can we calculate it? How can we compare it for the best understanding? Let's see it on this picture. You can see the tube, and you can see that, for example, the blood flow going from the first part to second part. We know that the pressure 1 will be more than the pressure 2, the pressure 2. This is a pressure gradient will be. And so, what happened? Let's continue this with the electricity. How? What about why the electricity must be? You can ask me. So, students, let's compare. For our conductor, we have a conductor and two parts of conductor. First and second will be the difference potential first and potential second, because electrons go through the conductor, like as our erythrocytes go through the tube. So, according to our if we take our knowledge about electricity, let's remember the electricity rules, and we know that there is the Ohm's law. And what is about fluid flow version of Ohm's law? The difference, or the pressure gradient between the first and second point, is the I multiply on R, like the difference potential, difference potential. What is about I? In electricity, this is the current. How much electrons or how much charges go through the conductor per unit time. So, what is here? How much erythrocytes go through the pipe, through the tube, through the vessels on time. So, like as in system international units can be millimeter divided by minute, liter divided by minute, or volume meter cube divided by second. And what is about R? In electricity, the resistance of the conductor, and in our tube, this is resistance of tube. And can we say and can we take it according to this formula? And what else? The resistance R is determined by the following formula, we can see, and the above flow equation becomes Poiseuille's law. Let's see on the slide. The formula denotes to us an important causal relationship between the volumetric second flow rate of fluid, of blood, and the pressure drop, gradient of P, across the tube at the ends of vessel. Even if the pressure at the ends of the tube of the vessel is very large, but the same, then the difference P is 0, and the flow or liquid or blood in the tube or in the vessel will not occur. But the more the difference between P, P1 and P2, the more key facts. The flow increases linearly with the pressure, and therefore to achieve a given perfusion in the capillary system, a sufficient pressure difference between them is required. The flow increases with force power of the radius of the pipe, force power of the radius, which is why narrowing blood vessels become so dangerous past a certain point, and flow decrease with the length AL. Long blood vessels have a greater resistance. Don't forget about it. This is the Poiseuille law. Poiseuille's law can describe us the connection between blood flow rate I. This is blood flow rate between resistance and pressure gradient, difference between P1 and P2. Don't forget about it. There are several ways to measure the viscosity. We said about physical characteristics of liquids, special equations, special laws, and now we must say about viscosity. And firstly, how can we calculate the viscosity? And there are several ways to measure the viscosity of a liquid. One of them is the Stokes method. This determines the viscosity of a liquid by the rate of sinking of a body. The density of the body material must be greater than the density of liquid, and otherwise it simply will not sink. For the best understanding of process, let's remember the composition of our blood. We talked about this at the beginning of this lecture. Yeah? Blood consists of plasma and bodies, most of which are erythrocytes, red blood cells, and there are leukocytes and platelets, don't forget. In our model, we will use balls as sinking bodies, for example, like as erythrocytes. When a solid ball moves in a liquid, or when a liquid stream follows around a stationary ball, the resistance force arises due to viscous friction between the layers of liquid that envelop the ball. Stokes found that this resistance force is equal to Stokes force is resistance force. How can we calculate it? We should take 6, multiply on pi, multiply on viscosity of liquid, multiply on the radius of the ball, of the erythrocyte, for example, and the velocity of the ball. So, let's remember now romantic part. Let's remember the sea with you. I think many of you have been to sea, and it seems to me that many of you walked in shallow water and also threw various stones and objects into water. Now your task is to remember how these objects were drowned. Let's remember. If you were attentive, you noticed that the immersion of the bodies had 2 stages. First stage and second stage. Like as in this model on the picture, you can see the ball which can go down in the tube, for example. The first stage is the stage when the object was moving quickly. There was an accelerated movement under the influence of the prevailing gravity. The force of gravity, F gravity, this is mg, and of the ball is directed vertically downwards. Archimedes force, F Archimedes, acts vertically upwards throughout the entire immersion of the ball. Since Archimedes force is less than gravity force, the balls begin to sinking faster and faster. But the faster it sinks, that greater the resistance force, Stokes force becomes. This force, according to the Stokes formula, is directly proportional to the speed and is directed in the direction opposite to the motion. So, when a certain speed is reached, the resultant of the three forces applied to the ball becomes zero, like as in this formula. And then, if you were attentive, the second stage began. When the speed or the velocity of the object stopped changing uniform movement. Obeying Newton's first law, the ball moves uniformly and rectilinearly while maintaining the previously achieved speed. Now we have many important tasks ahead of you to get the viscosity coefficient of fluid from our equation forces. How can be done? For more convince, we will do everything in order and write out each part of our equation. So, firstly, we can divide it on three parts because we have three parts in our equation. First part is gravity part. We know that we have the formula of density in our lecture. And density, how can we calculate the mass? Through the density. Mass of ball multiplied on gravity coefficient. We can put the formula of density, that's through the density, and put it in spite of mass, where is rho ball is the density of the ball material, and g is acceleration of gravity, and v is the volume of the ball. And from geometry, I think you know the volume of the ball is 4 divided by 3 and multiplying on pi r cube. Where is r? This is the radius of the ball. As a result, we have this part. So, second part, according to Archimedes' law, we know the formula of Archimedes' law. The density of liquid, multiply of the volume of ball, and gravity coefficient. So, don't forget. As a result, if we put the volume of ball again in spite of v, so will be this result. And the term Stokes formula, Stokes formula, we can take it from here, where we should take the radius of the ball and the velocity of the ball, and put our results into this formula in spite of our letters. And what happened? We will take this big equation. And if we use mathematics rules, and the only unknown in this equation was the water viscosity eta. And solving the equation from eta give us the design formula. Students, I don't know what happened, and this formula must be opposite. Must be opposite. I think may have problems with this, but how can we calculate viscosity coefficient? We should take coefficient 2, r radius in square, gravity, divide by 9 velocity, and multiply on difference between density of ball and density of liquid. Density of ball, density of liquid. This is the point or the formula. Can we calculate the velocity of liquid, and now you and I must consider a very important thing for any doctor. This is the measurement of blood pressure by Korotkov's method. For blood pressure, I think we know that as we used the thing is the pressure of blood in the arteries. This is certainly true, but there are some exceptions. Don't forget that we all walk on the planet And also don't forget that our planet is shrouded and in atmosphere, and the pressure of which is reported to us every morning by the weather forecast. And we remember that the normal atmospheric pressure is 760 millimeter mercury. This means that you and I must constantly overcome this pressure so that we can safely walk, breathe, swim in the sea, and perform all actions, different actions. Write the lecture, for example. This means that our arteries too must overcome external pressure so that their lumen remains open and free for the passage of blood. Therefore, in fact, we don't measure the arterial blood pressure itself, but how much it's greater than atmospheric. That is, we measure the difference between arterial and atmospheric pressure. Blood pressure is usually measured and expressed in two numbers: systolic blood pressure and diastolic blood pressure. Firstly, the upper number is systolic blood pressure. This is the maximum blood pressure in the generated waveform that stimulates the systemic circulation. And what is about diastolic pressure? This is the minimum arterial pressure in the wave pulse of systemic circulation. Don't forget this blood pressure has historically been measured in millimeter mercury again, yeah? And let's again that important to understand that we measure the difference between blood pressure and atmospheric pressure. So now we must say about Korotkov's method. For measuring arterial pressure, our difference, yeah, we use the Korotkov's method. This is the method, and this is the auscultatory method. To measure pressure with this method, we need a phonendoscope and a manometer that will measure the pressure in the cuff. Yes, you read that correctly, in the cuff, because we consider the pressure in the cuff to be equal to the pressure in the vessel that it compressed. The cuff is applied to the patient's right shoulder, 2-3 centimeters above the elbow band, and the phonendoscope membrane is applied to the patient elbow artery. In this case, your patient should be relaxed, calm before the measurement. Let's divide by blood pressure measurement into stages. For physics, we should divide it into 5 stages. The first stage, calm stage before measurement, and there is the laminar flow in the vessel. After that, we pump air into the cuff, squeeze the artery, there is no blood flow. We closed the artery, and the artery is clamped. What happened after? We begin to deflate. The moment comes when the heart is able to push blood through the partially compressed edge artery, let's see. And therefore, a pulse wave from the heart spreads along the walls of the artery, and we begin to hear tones, Korotkov sounds maybe. The first tone is systolic pressure, and you can see the normal numbers, yeah? And normal numbers are the different, and on the practice lesson I will say you again about it. And next stage, what happened? We continue to release air, therefore a turbulent flow of blood occurs in a partially pinched artery. Let's see. We hear tones and very quiet noise of turbulence, because will be the turbulence flow. And what happened after? We continue to release air, the artery straightens, the laminar flow of blood is restored, and all sounds disappear. And the last tone is the diastolic pressure on manometer, yeah? Normal number, we will talk about it on our practice lesson. And now you will watch an educational film on how to correctly measure blood pressure in a person. After you can see the physical base of this. Laminar and turbulent. Let's see the short video.
Hey everyone, it's Sarah with RegisteredNurseRN.com, and today I'm going to demonstrate how to check a blood pressure manually. First, you'll need to perform hand hygiene and gather your supplies. You'll need a stethoscope and a manual blood pressure cuff. So let's measure a blood pressure manually. To do that, we want to make sure our patient is sitting down with their arm at heart level and their legs are uncrossed. Now, if they're lying in bed, you would want to make sure that this arm is at heart level. Then what we're going to do is we are going to get our stethoscope and our blood pressure cuff. And you want to make sure you get the right size cuff for your patient's arm, because if you use too big of a cuff or too small of a cuff, it can throw off the reading. And what we're going to do is we're going to palpate the brachial artery, because this is the artery we're going to be listening to get our blood pressure, because we're going to be getting our systolic number, which is that top number, and this is the first sound we hear. And then our diastolic number, which is the bottom number, and this is the point where we no longer hear the sound. So whenever we're looking at the gauge of our blood pressure cuff, we want to make sure we're really noting those points, because it's going to tell us our systolic and diastolic number. So what we're going to do is we're going to put our cuff on our patient, and we want to make sure we find the brachial artery. This is the artery we palpate that we'll be using to determine our blood pressure. And it's found in the bend of the arm. So we're going to find it, and it is located here. And we're going to look on our cuff, and our cuff has these arrows. And because this is the left arm, we're going to make sure that this arrow is pointing in that direction of where that artery is. So you're going to put the cuff up about 2 inches above the bend of the arm. First, what we want to do is we want to estimate the systolic pressure. So we want to find that number. To do that, we're going to palpate the brachial artery, and we're going to inflate the cuff until I no longer feel the brachial artery. And at that point, when I no longer feel it, I need to make sure I'm looking at this gauge to know that number, because that number is our estimated systolic pressure number. Then when I go to take the blood pressure, I'm going to inflate the cuff 30 millimeters of mercury more than that estimated number. Now, the whole reason for doing that is because we want to avoid missing the oscillatory gap that can occur in some patients. Not all patients have it, but some. And it's usually patients with hypertension, because the oscillatory gap is like this abnormal silence that can occur, and it will throw off whenever you actually hear that first sound, which is your systolic number. So I'm inflating the cuff while feeling on the artery, and I'm going to note the point where I no longer feel the artery, which is about at the 100. Then I'm going to deflate it completely and wait about 30 to 60 seconds, and then we'll take the blood pressure. So our estimated systolic number is 100. Now I'm going to inflate the cuff to 130, and that will avoid missing the oscillatory gap if one was present. So I'm going to take my stethoscope, put it in my ears. You can use the bell or the diaphragm of your stethoscope. I like to use the bell because it's best at picking up low-pitched noises. So we're going to place that over the brachial artery. Do it lightly. Don't fully compress it, because you can occlude the artery. Then we're going to inflate our cuff to 130 millimeters of mercury. And we're going to let it fall about 2 millimeters of mercury per second. And we're listening for that first sound, which is our systolic number. Okay, it's 104. And we're listening for that last sound. And it was 78. So the blood pressure is 104 over 78. Then once you have your reading, make sure you fully deflate the cuff full of air, and you're going to take the cuff off of your patient, of course, and clean it if it's not disposable, and you will document the blood pressure and what arm you took it in. Now, what are normal blood pressure readings? According to the American College of Cardiology 2017 updated guidelines, a normal blood pressure is a systolic less than 120 and a diastolic less than 80. Elevated blood pressure would be considered a systolic of 120 to 129 and a diastolic less than 80. Hypertension stage 1 would be a systolic of 130 to 139 or a diastolic 80 to 89, and hypertension stage 2 would be a systolic greater than 140 and a diastolic greater than 90. Okay, so that is how to check a blood pressure manually. Thank you so much for watching. And
so students, thanks for the attention, and I will wait you on my next lecture. Goodbye.